Okay, so in this video we'll discuss work, energy and power, right? So yeah, let us just get into it. Ngizomane ngifunde ama notes lawa and then try to explain a few things as I go through, right? So this section is separated into work, energy and power, right? So this is a section for work. So what work is a scalar quantity and therefore does not have direction. The measuring unit of work is joule. The symbol of joule is J. Net work is the sum of all work done on an object. Net work is done by a net force, right? So when you're calculating net work, you are basically calculating the work done by some net force, meaning you'll add all the forces that are involved and then calculate work done by the net force. Or you can calculate the work done individually by each force and then after add the total work and then get net work, right? It will make more sense as we do some questions, right? And then but the positive work is the work done on an object to move it in the direction of the force. And then positive work increases kinetic energy of an object. Negative work is the work done by an opposing force, right? And then we see what negative work decreases kinetic energy of an object, right? So so these are some of the things to remember. Work is defined as the product of the force parallel to the movement of an object and the displacement of the object. So we can calculate work mathematically by saying work is equals to the force times the displacement time cos of an angle, where W is the magnitude of work, F is the magnitude of the applied force, and delta X is the magnitude of the displacement. Theta is the angle between the applied force and the displacement of the object. Okay, and then there's work energy theorem. So the work energy theorem states that the net work done on an object is equals to the change in the object's kinetic energy, right? And then the work energy theorem formula is W net is equals to delta K, or you can say W net is equals to delta E sub K. So this is just saying that the total work is the difference between the initial and the final kinetic energy. Okay, so let us do some example. Okay, so these are just basics, ne? We will do some more questions later on. Okay, so what a 220 Newton force is applied horizontally to a box of mass 50 kg which rests on a rough horizontal surface and the box moves 10 meters. The kinetic friction between the surface and the box is 40 newtons, and then they want us to calculate the work done on the box by the applied force, right? So let's sort of try to visualize the situation. So we have a 50 kg box. Let's imagine this is our 50 kg box, and then but a force is applied to the box, is applied horizontally to the box. So this force is applied horizontally, right? And then meaning if it's applied horizontally, the angle between the force and the displacement of this object will be 0, because the force is applied horizontally and the box is resting on a horizontal surface, right? So the force, the angle between the applied force and the displacement will be 0. Therefore our theta will be 0 degrees. So now they want us to calculate the work done on the box by the applied force. So we know that the applied force is equals to 220 newtons. So the work done by the applied force will be equals to the applied force times the displacement of the object times cos of the angle. The angle is that one between the force and the displacement, right? So the force is 220, the displacement is 10 meters, and then cos theta is 0 degrees. So if you just punch this in your calculator, you'll see Uti, this is 2200 joules, right? And then this is question 1. Question 2, but he calculate the work done on the box by the normal force. So the normal force is the force exerted by the surface on the box. So we know Uti, that normal force is exerted vertically, or it's perpendicular to the displacement of the object. And then we know the magnitude of the normal force is equals to the magnitude of the direction of the gravitational force. So because of Newton's third law of motion, the weight of the box exerts a force on the surface, and then the surface will exert the same force in the opposite direction, right? So meaning these two forces will be the same, they are just acting in opposite direction. So the box exerts a force on the surface, and at the same time the surface exerts an equal force onto the box in the opposite direction. So now to calculate the normal force, let's say it's F normal, Fn for normal force will be mg, the mass of the box times the gravitational acceleration will give us the normal force, right? So this is 50 times 9.8. Okay, so 50 times 9.8 is 490 newtons. So now that we have the magnitude of the force, of the normal force, we can calculate the work done by the normal force on the object. So notice this force is perpendicular to the displacement of the object. So our theta for the normal force will be 90 degrees. So now calculating the work done by the normal force will say it is the normal force times the displacement times cos of the angle theta, right? So the normal force is 490 newtons, the displacement is still 10 meters, and then our theta is 90 degrees because the normal force is perpendicular to the displacement, right? So if you say cos 90 in your calculator, you'll see what it's 0. So therefore the entire thing is 0 joules, meaning the normal force is not doing any work on the object because it's perpendicular to the displacement, right? Okay, so let us go on to question 3. So question 3, calculate the work done on the box by the frictional force, or the work done on the box by the frictional force. Okay, so we are told in the question the kinetic friction between the surface and the box is 40 newtons. So there's a frictional force of 40 newtons acting in the opposite direction to the motion of the object. Okay, so we know the magnitude of the frictional force, which means we can calculate the work done by the frictional force. Also note the angle between the frictional force and the displacement of the object is 0. Therefore our theta will be 0 degrees. So now the work done by the frictional force will be equals to the magnitude of the frictional force times the displacement times cos of our angle theta. So the magnitude is 40. Sorry, here I said the angle between the frictional force and the displacement of the object is 0, but then it's not 0, it will be 180 since the frictional force is acting in the opposite direction to the displacement of the object. Remember that displacement is a vector quantity, therefore it has direction. So now the frictional force is acting in the opposite direction to the displacement of the object. So the angle between this force and the displacement will be 180. So we have our frictional force 40, our displacement is still 10, and then our theta will be 180. So this will be minus 4,000 joules. Okay, and then question 4, what you calculate the net work done on the object, on the box. So the net work done on the box is the work done by the net force. So you can start by calculating the net force, which is the applied force plus the frictional force, right? So the applied force is 220, the frictional force is 40 newtons. So this will be 220 minus 40, it will be 180 newtons. So now the net force is 180 newtons, and it's acting in the direction of the displacement of the object, and the angle between this net force and the displacement will be 0. So the work done by the net force, the net work done will be the magnitude of the net force times the displacement times cos of our angle theta. So the net force is 180, the displacement is still 10, our theta will be 0 degrees. So this will be 1,800 joules, right? And then question 5, calculate the net force acting on the object and the work done by the net force. So question 4, 5, 6 sort of like the same thing, because the way to calculate the network, you can say oops, right. Oh. So the way to calculate network, you can say it's W net is equals to F net delta X cos theta. Okay, or you can say W net, where F net here is the sum of the applied force and the frictional force, or you can say W net is the work done by the applied force plus the work done by the frictional force. These two will give you the same answer. Okay, they will give you the same answer. Okay, so on this question, but a crate of mass 40 kg slides down a rough incline that makes an angle of 20 degrees with the horizontal, as shown in the diagram below. The crate experiences a constant frictional force of magnitude 190 during its motion down the incline. So the forces acting on the crate are represented by R, S, and T. And then question 1, they want us to label the forces. So we see the R is the normal force. It is perpendicular to the displacement of the object, or it is perpendicular to the surface, right? So R is the normal force, and then S is the gravitational force, X is the force of gravity, and T is the force of friction, right? And then question 2, they want us They say the crate passes point A at a speed of 2 meters per second and moves a distance of 12 meters before reaching point B lower down on the incline. They want us to calculate the net work done on the crate during its motion from point A to point B. The net work done on the crate from point A to point B. Right, so we know that the forces acting on this crate is the force of friction, the force of gravity, and the normal force. But because the normal force is perpendicular to the displacement of the object, we know it follows that it is not doing any work. It is not doing any work on the object, since cos of the angle 90 degrees will be 0, meaning the net work done there is 0 joules, the net work done by the normal force. So we are only interested in the work done by the force of gravity, and we are only interested in the work done by gravity and friction, right? So we will say W net is equals to the work done by the force of gravity, which is S, plus the work done by the force of friction, which is T, right? So the work done by the force of gravity is the force of gravity, which is mg, times the displacement times cos of an angle theta, plus the work done by the force of friction will be the force of friction, it will be, so it will be the force of friction, which is T, times the displacement times cos of an angle theta, right? So now mg is this force of gravity S. Mg is the force of gravity. So m is the mass of the crate, which is 70. G is the gravitational acceleration, and the displacement is 12 meters, and cos theta. Now we know what theta is, the angle between the force and the displacement of the object. So in this case, the angle between the force of gravity and the displacement of the object is this angle here, right? It's this angle here. So now to get the magnitude of this angle, we'll sort of like formulate a triangle, and you know what this will be 90. So this angle here will be 180 minus 90 minus 20. This angle will be 70 degrees. So the angle between the force of gravity and the displacement is 70 degrees. So there you say cos 70, right? So now this is work done by the force of gravity, and then you need to add the work done by the frictional force. So the magnitude of the frictional force is 190, the displacement is still 12, and then the angle between the frictional force and the displacement of the object is 180. So there you will say 180. And then when you punch this in your calculator, you'll get to it's 70 times 9.8 times 12 cos 70 plus 190 times 12 times cos 180. So this will be this will be 535.51 newtons, joules. It will be 535.51 joules. So another way of doing this question, you can first calculate the net force, right? And then after calculating the net force, you will calculate the work done by the net force, which is W net. So now the net force will be the force of friction plus the gravitational force which is parallel to the displacement of the object. Now if you sort of draw a free body diagram, you will have that this is the force of gravity, this is the force of friction, this is the normal force, and then here you'll have a normal force, or you'll have Fg parallel, right? This is the force of Fg perpendicular. This is the force of gravity perpendicular to the displacement of the object. And then here you'll have the force of gravity which is parallel to the displacement of the object. Now this is the force which actually does work to the object since it's parallel to the surface. So that force will be here. And then the angle of interest, so to get the magnitude of this Fg parallel, you will use this angle here, right? So you will use this angle here, and then now to get that angle you will say sine 20. Sine 20 will be Fg over Fg parallel. So sine 20 Fg sine 20, so this will be Fg parallel, eh? This side will be Fg parallel, this side will be Fg. So sine 20 will be Fg over Fg parallel. So now we want the magnitude of Fg parallel. Fg parallel will be Fg over sine 20, where Fg is equals to mg, right, which is the mass of the object times 9.8 divided by sine 20. We'll get what the Fg parallel is 70 times 9.8 divided by sine 20. Fg parallel will be 2005.73 newtons. Now this is the gravitational force which does work on the object, right? So now to calculate the net force, it will be the frictional force, which is 190, plus Fg parallel, which is 2005.73, right? And then the net force acting on the object will be the net force acting on the object will be 1815.73, right? Sorry, like in I just want you guys to get the idea, right? So there's two ways of calculating this. You can calculate it using the work done by each force, or by first calculating the net force and then after calculate the work done by the net force, right? So let me erase some stuff. Right, so this is 1815.73 newtons, the net force, right? So this is the net force. Now the work done by the net force is F net delta x cos theta. So it will be 1815.75 times 12 times cos 0, right? This is not right. Okay, so kule method yesi2 like le ndlela engicalculate ngayo u-FG parallel akusiyo, right? So what I was supposed to do is bekumele draw i-angle bekumele draw a-free body diagram, and then la gravitational force we have the perpendicular and the parallel component of this force, right? So the one that we are interested in is the parallel force, since the perpendicular one won't do any work on the object, since it's perpendicular to the motion or to the displacement of the object. So now if we sort of draw a free body diagram of this whole scenario, we'll see what this is our friction, which is T. This will be our gravitational force, which is S, and this will be our normal force, which is R, right? And then on this gravitational force, there is a perpendicular and parallel component of this force, right? So the perpendicular component will be this one, and the parallel one will be this one, right? And then that angle between the perpendicular and that angle between the perpendicular component and the actual gravity will be the angle theta. In this case, it will be 20 degrees, right? I think you should remember this from grade 11, right? When you are given inclined plane, you know what this gravitational force has a perpendicular component and a parallel component. So in this case, the parallel component is this one, and the perpendicular component is this one, right? So now we are interested in calculating this one, since it will be the one which does work on the object. The one which is perpendicular to the displacement of the object won't do any work. So now we want S parallel, right? So now to calculate S parallel, you'll see what if you say sine 20, this is 90 degrees here. If you say sine 20, it will be opposite of hypotenuse. So sine 20 will be S parallel over S, right? And then to calculate S parallel, you will say it's S times sine 20, right? Where S is the gravitational force, which is mg, where m is the mass, 70, and g is the gravitational acceleration, 9.8, and then you say sine 20 there, right? And then this force is equals to 234.63 newtons, right? It's 234.63 newtons, right? So yeah, now from here we can calculate the net force acting on the object, right? We can say F net is equals to S parallel plus the force of friction, which is T. So this will be 234.63 plus minus 190, the force of friction. So this will be 234.63 minus 190 is 44.63. This will be 44.63 newtons. Okay, now that we have the net force acting on the object, we can calculate the net work done on the object, which means the work done by the net force on the object. So you will say W net is equals to the net force times the displacement times cos of the angle theta, right? So now theta will be 0, since like the net force is parallel to the displacement of the object. So the angle between the net force and the displacement of the object will be 0, right? So here I would have 4.63 times 12 times cos 0 degrees, right? So this will be 535.56 joules, Remember, with our previous method, the answer was 535.51, which are very close. So you can do this ngendlela ezihlukile. First, you can calculate the work done by each force and then combine the two and get your net work done. So first you can calculate the work done by friction, and then calculate the work done by the gravitational force, and then add the two to get your net work done. Or you can first start by calculating the net force of acting on this object and then calculate net work done. So yeah, there are two approaches to this. You can choose either one, but then yeah, you'll make the choice. Okay. Okay, so the question, but a rescue helicopter is stationary, that is, it hovers above a soldier. The soldier of mass 80 kg is lifted vertically through a height of 20 meters by a cable at a constant speed of 4 meters per second, right? The tension in the cable is 960 newtons. Assume that there is no sideways motion during the lift. Air friction is not to be ignored. And then question 1, what is state the work energy theorem in words, right? So mathematically, this is the work energy theorem. The work done on an object is equals to the change in kinetic energy of the object, right? So in words, you'll just read this equation. You'll say the net work done on an object is equals to the object's change in kinetic energy. Yeah, so that is the work energy theorem in words. So mathematically, this is the work energy theorem. In words, you'll say the net work done on an object is equals to the object's change in kinetic energy. That is the work energy theorem, right? And then question 2, but it draw a labeled free body diagram showing all the forces acting on the soldier while being lifted upwards. So you'll know what you'll represent. Any free body diagram will represent the object by a dot, in this case the soldier, and then you'll represent all the forces by arrows. So now we see Lapa on the picture with him. There's a force lifting the soldier upwards, which is 960. So this is the tension force. And then we know with him, there will always be a force pulling down this soldier. And they did mention with it there's some friction. So the force pulling down the soldier is his weight or the force of gravity. And then this one is air friction. So on your free body diagram, you'll have tension, and then you'll have the force of gravity, Fg, and then you'll have the force of friction, the force of air friction, right, which is Ff, right? And then question 3, but write down the name of a non-constant force that acts on the soldier during the upward lift, right? So if we check this, the soldier is being pulled up at a constant speed by a cable, right? So we know with okay, it probably means the tension force is constant throughout until the soldier gets to the helicopter. And we also know what the mass of the soldier won't change while he's being lifted up. Therefore, the gravity of the soldier will not change because the weight, there's the difference between mass and weight, right? So weight is equals to mass times gravitational acceleration, which is weight. This is weight, that is mass. So the weight of the soldier depends on the mass. So if the mass of the soldier is constant throughout, it means the weight of the soldier won't change, meaning this force won't change, the force of gravity won't change. So which leaves us with air friction. So the force which won't be constant is air friction. Okay, and then question 4, they say use work energy theorem to calculate the work done on the soldier by friction after moving through the height of 20 meters. So work energy theorem, but use work energy theorem. This is work energy theorem. Therefore, you will say W net is equals to the object's change in kinetic energy. So now, because the soldier is being lifted up at a constant speed, it means he is not accelerating. So if he's moving at a constant speed, there is no change in kinetic energy there, because remember, a kinetic energy is change in kinetic energy is the initial kinetic energy, the final kinetic energy minus the initial kinetic energy, right? And then we know what the final kinetic energy will be 1 over 2 mvf squared minus 1 over 2 mvi squared. The initial velocity, final velocity, initial velocity. Now, if the soldier is being pulled up at a constant speed of 4 meters per second, it means constant speed, it means the initial and the final velocity are the same. Therefore, these two quantities will be the same. The final and the initial kinetic energy will be the same. So which means you'll be saying this number minus some other equal number, which will leave you to 0 joules. Therefore, there is no change in kinetic energy because of constant speed, right? So which means the net work done is 0 joules, right? So we know what the net work done is equals to the sum of the work done by each of the individual forces. So we'll say the work done by tension plus the work done by gravity plus the work done by friction is equals to 0. This is net work done. This is net work done. Ne? Now you will calculate the work done by tension by saying it is the tension force, which is 960, times the displacement, which is 20, times cos of an angle. In this case, the angle will be 0 since this tension force is in the same direction as the displacement of the object. So this will be 0 degrees, plus the gravitational force, which is the mass of the soldier times the gravitational acceleration times the tension force, times the displacement times cos of an angle, cos 180 in this case, since this force is acting in the opposite direction to the displacement of the object, right? And then plus the work done by friction is equals to 0. Now we want to solve for WF. Okay, so in your calculator you can just punch this whole thing and then you'll have WF. Alright, so you'll say 960 times 20 times cos 0 plus 80 times 9.8 times 20 times cos 180. So this will give you 3520 joules, meaning the work done by friction will be minus 3520 joules, right? And then question 5, identify two forces which do negative work. So the forces that do negative work on an object are those forces which act in the opposite direction to the displacement of the object. Meaning, if the object is moving upwards and there are forces which are acting downwards, these forces are doing negative work on the object. So from our free body diagram, we can see there are two forces acting against the motion of the object. So those forces are friction and gravitational force. Friction and gravity. The gravitational force and the force of friction, right? So we are done with this question. So next up we'll do energy. So far we were discussing work. Remember, until the section is divided into work, energy and power. So far we have covered work. Next up we need to cover energy, and then after cover the power. And then after we are done with all this, we will attempt past papers. Okay.